Good evening, students. Am I audible? Guys, am I audible? Hello. கேக்குதாப்பா?
Sir, yes, sir.
ஓகே. தம்பி உங்களுக்கு அசைன்மெண்ட் வந்து கூகுள் கிளாஸ் ரூமில் போஸ்ட் பண்ணியிருக்கேன். ஸோ நாளைக்கு நைட்டுக்குள்ளே அசைன்மெண்ட் வந்து நீங்கள் எழுதி சப்மிட் பண்ணிடுங்க. ஸோ அந்த அசைன்மெண்ட்டை பேஸ் பண்ணி தான் உங்களுக்கு இன்டர்னல் மார்க் வந்துருக்கு. ஸோ உங்கள் இன்டர்னல் டெஸ்ட் மார்க்கோட ப்ளஸ் அசைன்மெண்ட் மார்க் சேர்த்து தான் வந்து யூனிவர்சிட்டி எண்ட் செமஸ்டர் எக்ஸாம் நீங்கள் எழுதுறதுக்கு போகிறப்ப அந்த மார்க் உங்களுக்கு வந்து அதை பேஸ் பண்ணி தான் போடுவோம். ஸோ அசைன்மெண்ட் வந்து நான் கூகுள் கிளாஸ் ரூமில் போஸ்ட் பண்ணியாச்சு. ஸோ நாளைக்கு நைட்டு 10 o'clock நீங்கள் எழுதி அப்லோட் பண்ணிடுங்க அசைன்மெண்ட். ஓகேங்களா? Okay guys, today we are going to discuss about CAN. So this is shortly called as CAN, Control Area Network. This is called as Control Area Network. So this is mostly used in automotive system to connect each and every parts components into ECU. Okay, so this is plays important role in automotive vehicle system. So this controller area network is a serious network technology that was originally designed for the automotive industry, especially for European cars, but has also become a popular bus in industrial automation as well as other applications. So this CAN bus is primarily used in embedded system. It is CAN primarily used in the embedded system, and as its name implies, is a network technology so that provides fast communication among microcontrollers up to real time requirements, eliminating the need for much more expensive and complex technology of a dual port RAM. So the CAN is a two wire. Okay, the CAN is a two wire half duplex and high speed network system that is for superior to conventional serial technologies such as RS-232 in regards to functionality and reliability, and yet CAN implementation and more cost effective. So this controller area network is going to interface with the hardware. Okay, so we can use so many hardwares so that hardwares can be interfaced with itself. CAN networks can be used as an embedded communication system. Embedded communication system for microcontrollers as well as an open communication system for intelligent devices. Some users, for example, in the field of medical engineering, opted for CAN because they have to meet particularly stringent safety requirements. Similar requirements had to be considered by manufacturers of other equipment with very high safety or reliability requirements. So that is robots, lifts, and the transportation system and other automotive vehicles. The greatest advantage of a CAN controller area network lies in the reduced amount of wiring combined with an ingenious prevention of message collision. That means meaning no data will be lost during message transmission. Okay, we need to know overview of CAN's technical characteristics before entering into this topic. CAN is a serial networking technology for embedded solutions, and it needs only two wires named CAN H and CAN L. and operates at data rates up to 1 megabyte per second and support a maximum of 8 bytes per message frame, and does not support node IDs, only message IDs. One application can support multiple message IDs. And it will support message priority, that is, lower the message ID, the higher its priority. And it supports two message ID lengths, for example, 11 bit, so that is standard, and 29 bit, so that is extended, and does not experience message collisions. And the CAN is not demanding in terms of cable requirements. Twisted pair wiring is sufficient. Okay, the CAN is plays a vital role in automotive vehicle system to connect each and every component, sensors and actuators. Okay, the sensors and actuators in the automotive system and vehicle to bring the data as fast as possible with the help of this CAN. Okay, this devices the CAN the vehicle bus standard designed to allow the microcontrollers and devices to communicate with each other's applications without a host computer. It is a message-based protocol, and it is designed originally for multiplex electrical wiring within automotive to save on copper. But it can also be used in many other contexts. For each device, the data in a frame is transmitted sequentially, but in such a way that if more than one device transmit at the same time, the highest priority device can continue while others back off. Okay, the important application of this CAN is important application of the CAN is passenger vehicles, trucks, buses, agricultural equipment, electronic equipment for aviation and navigation, industrial automation and mechanical control, elevators, escalators, building automation, medical instruments and equipment, model railways, railroads, ships and other maritime applications, lighting control system. These are all important applications of the CAN. In automotive, the modern automobile may have as many as 70 electronic control units for various subsystems. Traditionally, the biggest processor is the engine control unit. So others are used for autonomous driving, advanced driver assistance system, transmission, airbags, anti-lock braking, airbag system, cruise control, electric power steering, audio system, power windows, doors, mirror adjustment, battery and recharging system for hybrid and electric cars, etc. So some of these form independent subsystem, but communications among others are essential. A subsystem may need to control actuators or receive feedback from sensor. Okay, the CAN standard was devised to fill this need. One key advantage is that interconnection between different vehicle system can allow a wide range of safety, economy, and convenience features to be implemented using this software alone. Okay, we can auto start and stop, electric park brakes, parking assist. So many things we can achieve when we are going to use this CAN. Okay, the CAN protocol has been used on the Shimano D12 electronic gear shift system for road bicycles since 2009. The CAN buses is also used as field bus in general automotive environments. The manufacturers, including Nismo, the so many manufacturers are there. They are using the CAN. Okay, the data transmission. So now you just look into this before CAN engine control, transmission control, active suspension, and everything is going to connect it to the dashboard and the lighting. So many things are going to connected with the dashboards. You can see the lighting, air condition, power locks, air brakes, power windows, power seats. These are all connected with the dashboard before the CAN is implemented. So this is with CAN. So only one line is going to interconnected with all the parts. Okay, we are going to use only a single line, only two wire system. So that is connected with the CAN control area network. Okay, because of the solution to this problem was the connection of the control system via serious bus system. Okay, in this system, so we are we have only one, for example, only one line. So with that line, we have connected all the sensors and actuators and all the electronic components which will obey the ECU commands. Okay. This bus had to fulfill some special requirements due to its usage in the vehicle. So with the use of CAN, so the point-to-point wiring is going to replace by one serial bus connecting all control system. This is accomplished by adding some CAN specific hardware to each control unit that provides the rules or protocol for transmitting and receiving the data. The CAN data transmission uses lossless bitwise arbitration method of contention resolution. This arbitration method requires all nodes on the CAN network to be synchronized to sample every bit on the CAN network at the same time. This is why some call CAN synchronous, and unfortunately, the term synchronous is imprecise since the data is transmitted in all asynchronous format, namely without a clock signal. The CAN specifications uses terms dominant bits and recessive bits, where the dominant bit is a logical 0. So this is actively driven to a voltage by the transmitter, and the recessive is a logical 1. This is passively written to a voltage by a resistor. So this is the with CAN. So you can see the high speed and low speed, and the CAN is going to connect it everywhere. Engine control, anti-lock brakes, and the transmission control, active suspension. So these are all connected with high speeds, lighting and air conditioning, power locks and airbag, and power windows, seats. So these are all the connected with the low speed. These are all considered for the low speed. So this is another small video for understanding the practical understanding of how the CAN is used in most of the automotive vehicle system, how it places.
Therefore, we decided to launch a series of simple CAN intro articles written by one of our non-engineers to make sure it stays simple. Enjoy. What's CAN bus all about? Imagine that your car is like a human body. The controller area network system, CAN bus, is the nervous system, facilitating communication between all parts of the body. Similarly, nodes, or electronic control units, ECU, are connected via the CAN bus, which acts as a central networking system. In an automotive CAN bus system, ECUs can, in example, be the engine control unit, airbags, or the audio system. A modern car can have up to 70 ECUs. This is where the CAN standard comes in handy, as it allows ECUs to communicate with each other without complex, dedicated wiring in between. In turn, this allows for several features to be added via software alone. An example, electronic gearbox control. Indeed, that is the primary purpose of CAN, to allow any ECU to communicate with the entire system without causing an overload to the controller computer. But why is CAN so popular? 5 key reasons. 1. Low cost. ECUs communicate via a single CAN interface. In other words, not analog signal lines, reducing errors, weight, cost. 2. Centralized. The CAN bus system allows for central error diagnosis and configuration across all ECUs. 3. Robust. The system is robust towards failure of subsystems and electromagnetic interference, making it ideal for, an example, vehicles. 4. Efficient. CAN messages are prioritized based on IDs so that the highest priority IDs are non-interrupted. Critical. An example, vehicles. 5. Flexible. Each ECU contains a chip, allowing it to receive all transmitted messages, decide relevance, and act accordingly. This allows easy modification and inclusion of additional nodes such as CAN bus data loggers. The CAN bus history in short. Pre-CAN car ECUs relied on increasingly complex point-to-point wiring. 1986, Bosch developed the CAN protocol as a solution, releasing it at a SAE Congress. 1991, Bosch published CAN 2.0 inclusion, CAN 2.0A 11-bit, and CAN 2.0B 29-bit. 1993, CAN is adopted as international standard, ISO 1189-8. 2012, Bosch released the CAN FD 1.0, aka CAN with flexible data rate, Today, almost every new European car comes with a CAN bus system, and it is used broadly in trucks, buses, industry vehicles, ships, planes, and industrial automation. Further, more exotic cases include drones, radar systems, submarines, or even prosthetic limbs. Looking ahead, the CAN bus system will stay relevant, and most likely even more so with the rise of example cloud computing, Internet of Things, IoT, and autonomous vehicles. What does a CAN message look like? To understand how the CAN bus system works, let's break down the messages sent over the network. The 11-bit identifier, CAN 2.0A messages, look similar, but with shorter CAN IDs. The 8 key parts of a CAN message are as follows. SOF. The start of frame is a dominant 0 to tell the other ECUs that a message is coming. CAN ID contains the message priority as well as functional address, an example, RPM, wheel speed. RTR, the remote transmission request, allows ECUs to request messages from other ECUs. Control informs the length of the data in bytes, 0 to 8 bytes. Data contains the actual data values, which need to be scaled or converted to be readable and ready for analysis. CRC, the cyclic redundancy check, checks data integrity. ACK, the ACK slot indicates if the CRC process is okay. EOF marks the end of the CAN message. That's a lot, but only 3 are practically relevant in most data logging scenarios: the CAN ID, the control, and the data field. This is also why you typically only see these in CAN bus data output. CAN provides the basis for communication, but not a lot more. For example, the CAN standard does not specify how to handle messages larger than 8 bytes or how to decode the raw data. Therefore, a set of standardized protocols exists to further define how data is communicated between ECUs of a given network. Some of the most commonly encountered standards include SAE J1939, OBD2, and CAN Open. SA J1939. This is the standard in vehicle network for buses, trucks, and other heavy-duty vehicles. All J1939 messages rely on the extended 29-bit CAN identifier. Further, J1939 data parameters, an example RPM, vehicle speed, are identified by a suspect parameter number, SPN, which are in turn grouped in parameter group numbers, PGN, containing 1 plus SPNs. With this standardized structure, CAN messages from example buses and trucks can be scaled and decoded into readable data using parameter tables from the J1939 standard. Further, several standards are derived from J1939, including, an example, the Fleet Management System, FMS, which is freely available and included in Canvas. For more information, see our simple intro to J1939 or our J1939 ID to PGN converter. OBD2. Onboard Diagnostics, OBD, is a self-diagnostic and reporting capability that, an example, mechanics use to identify what is wrong with your car. The OBD2 standard specifies a number of standardized diagnostic trouble codes, DTCs, which can be retrieved by a CAN logger or diagnostics tool for any vehicle. But what makes OBD2 really interesting? OBD2 supports data on many basic real-time parameters, an example, vehicle speed, RPM, fuel consumption. This means that OBD2 is also used for an example, real-time vehicle telematics or post-analysis using CAN data loggers. Applications include vehicle fleet management, fuel optimization, proactive vehicle diagnostics, and more. To log OBD2 data, the CAN logger must request the data by submitting pre-specified CAN frames with specific parameter IDs, PID, to the CAN bus. When using the CAN logger X000, this can easily be configured in Canvas. For basics on OBD2, check out our simple intro to OBD2, or check our practical guides to logging OBD2 data or streaming it in Wireshark. CAN Open. CAN Open is used widely, an example, industrial automation applications. It builds on CAN in terms of physical layer, an example, lines used, voltages. and the data link layer, an example utilizing a CAN frame message based on protocol. In practice, this means that a data logger, like the CAN logger X000, is able to log data from CAN open applications, though the method of X-post data conversion will vary depending on the specific application. Our Intel page contains several intro articles, uses cases, and guides. Let us know if you have more suggestions for the series.
Welcome to Automotive Basic Knowledge. Now our topic is about automotive CAN bus system. In this discussion we covered controller area network system, CAN bus output signal, CAN bus components, CAN data transfer process, CAN bus data message structure, how the CAN system works, controller area network system. The controller area network, CAN, also known as CAN bus, is a vehicle bus standard designed to allow electronic control units and devices to communicate with each other and applications without a host computer. As an alternative to conventional multi-wire loops, CAN bus allows various electronic components, such as electronic control units, microcontrollers, devices, sensors, actuators, and other electronic components throughout the vehicle to communicate on a single or dual wire network data bus up to 1 megabit per second. The CAN bus is a message-based protocol designed originally for multiplex electrical wiring within motor vehicles, but also can be used in many other contexts. Figure 1 shows a simplified schematic diagram of the CAN system and shows some of the possible units, devices that can be connected onto the CAN bus. CAN bus output signal. Typically the CAN bus is made up of two wires, CAN H and CAN L, which connect to all the devices in the network. The signals on the two CAN lines have the same sequence of data, but their amplitudes are opposite. So if a pulse on the CAN H line goes from 2.5 volts to 3.75 volts, then the corresponding pulse on the CAN L line goes from 2.5 volts to 1.25 volts, opposite than CAN H. By sending the data in equal and opposite ways like this allows for greater noise immunity and therefore a less chance of the data being corrupted. Figure 2 shows CAN H and CAN L differential output. Status of bit with the value 0 equals 2.5 volts, differential voltage equals dominant state. Status of bit with the value 1 equals 0 volts, differential voltage equals recessive state. CAN bus components. Figure 3 shows an example of two connected devices as well as the components that make up a CAN bus, CAN controller, CAN transceiver, two data bus terminals, R, and two data bus lines, CAN high line and CAN low line. Figure 3 shows CAN bus components. CAN controller receives the transfer data from the microcomputer integrated in the control unit, device, also known as CAN node. The CAN controller processes this data and relays it to the CAN transceiver. Also, the CAN controller receives data from the CAN transceiver, processes it and relays it to the microcomputer integrated in the control unit, device, CAN node. CAN transceiver is a transmitter and receiver in one. It converts the data which the CAN controller supplies into electrical signals and sends this data over the data bus lines. Also, it receives data and converts this data for the CAN controller. CAN data bus terminal is a resistor, R, typically of 120 ohms. It prevents data sent from being reflected at the ends and returning as an echo. CAN data transfer process. The CAN data transfer process consists of the following stages: supplying data, sending data, receiving data, checking data, and accepting data. Figure 4 shows CAN bus data transfer process. Supplying data, the CAN node provides data to the CAN controller for transfer. Sending data, the CAN transceiver receives data from the CAN controller, converts it into electrical signals and sends them back into the network. Receiving data, all other CAN nodes networked with the CAN data bus become receivers. Checking data, the CAN node checks whether they require the data they have received for their functions or not. Accepting data, if the received data is important, it is accepted and processed. If not, the received data is ignored. There are two different types of standards for CAN systems that relate to the physical layer: ISO 3 low speed can up to 125 kilobits per second, distance up to 500 meters, and ISO 11898 2 high speed can up to 1 megabit per second, distance up to 40 meters. The CAN system is further divided into two formats for the message frames 2.0a and 2.0b. The two standards differ in the size of the identifiers, ID. Standard CAN, version 2.0a, uses 11-bit identifiers in the arbitration field. Extended CAN, version 2.0b, supports a length of 29 bits for the identifier, made up of the 11-bit identifier, base identifier, and an 18-bit extension. CAN bus data message structure. Figure 5 shows the CAN bus data message structure. The basic structure of the message is the same for both standard and extended version. Figure 5 shows CAN bus data message structure. SF equals start field indicates the beginning of a message with a dominant bit, so this field marks the start of the data protocol. A bit with 3.75 V, depending on the used system, is sent over the CAN H line, and a bit with 1.25 V is sent over the CAN L line. That is, the differential voltage is 2.5 volts. See Figure 2. Message identifier defines the level of priority of the data protocol. If, for instance, two CAN nodes want to send their data protocol simultaneously, the CAN node with the higher priority takes precedence. The lower the value, the higher the priority of the message. As stated earlier, depending on the standard being used, the length of the frames can be in two formats: standard, which uses an 11-bit arbitration ID, and extended, which uses a 29-bit arbitration ID. Control, also known as check field, displays the number of items of information contained in the data field. This field allows any receiver to check whether it has received all the information transferred to it. Data field. In this field, the information is transferred to the other CAN nodes. CRC equals cyclic redundancy check, also known as safety field, contains 15-bit cyclic redundancy check code and a recessive delimiter bit. The CRC field is used for transfer faults detection. ACK equals acknowledge field, also known as confirmation field. In this field, the receivers signal to the transmitter that they have correctly received the data protocol. If an error is detected, the receivers notify the transmitter of this immediately. The transmitter then sends the data protocol again. F equals end field. This field marks the end of the data protocol. This is the last possibility to indicate errors which lead to a repeat transfer. Summary of how the CAN system works. As stated earlier, at the CAN system there is no master that controls when individual CAN nodes have access to read and write data on the CAN bus. When a CAN node is ready to transmit data, it checks to see if the bus is busy and then simply writes a CAN frame message onto the network. The CAN frames that are transmitted do not contain addresses of either the transmitting node or any of the intended receiving nodes. Instead, an arbitration ID that is unique throughout the network labels the frame. All CAN nodes on the CAN network receive the CAN frame, and depending on the arbitration ID of that transmitted frame, each CAN node on the network decides whether to accept or ignore the received frame. If multiple CAN nodes try to transmit a message onto the CAN bus at the same time, the node with the highest priority, lowest arbitration ID, automatically gets bus access. Lower priority CAN nodes must wait until the bus becomes available before trying to transmit again. In this way, you can implement CAN networks to ensure deterministic communication among CAN nodes. The table below shows an example of how the information of engine coolant temperature can be transferred with 1, 2, and 3 consecutive bits and respectively 2, 4, and 8 possible variations. The higher the number of bits, the more items of information can be transferred. The number of possible items of information doubles with each additional bit. If you enjoyed reading and watching this video, please let me know. Click the like button or provide your comment below. Thank you.
Okay, guys, I think you have better understanding of the CAN network and where CAN is used and how the data is going to transfer and what are the various types of CANs and functions, everything you have seen. So with that, I'm going to conclude my session. So if you have any doubt, you can ask. So otherwise, we can left from the meeting, and you should complete the assignment what I have assigned in your Google Classroom. So you should write and submit the scanned copy of the answer, the assignment copy in Google Classroom on or before 6/17/9/2021 before at 10 p.m. on tomorrow. Okay, don't forget it.